You all can still hear me? Okay. Thank you so much, Kim. That was just lovely, as usual.
Thank you so much for having me.
Yeah, well, it's really a pleasure every month. And I know we get comments. I hope you look at the comments. We are not the only ones that enjoy it.
So thank you so much for having me. I decided to make it more kind of meditation tonight. And hopefully, thank you so much for having me.
Yeah, well, thank you for playing. And I guess it's time to actually start our meeting. So, do we change over? I guess we have. Welcome everybody to the, if you can believe it, June meeting of Orange County Astronomers. We're in month 6 of the 2021 year, and delighted to have you with us. As always, we have a excellent program, which I would like to, we don't say it often enough, but Raisa, we really thank you very much for putting it all together. We know that we would not have nearly the smoothness of program or the content without all of your efforts. Thank you very much. And with that, I guess I should turn it over to the next phase, which is the club announcements. And I believe Kyle is leading off with that. Am I right?
Yep. Here we go. Hold on, let me share. Let's share first, that'll help. All right, so I believe Cecilia is going to start off with the announcements tonight. Go ahead.
And welcome to members. We hope you enjoy this amazing meeting that we all put together. So star parties are still on hold. I know that we're all getting vaccinated, so it's actually a great time because everything's starting little by little. So it's a great time. Probably by fall, we should be more events on ground. So it's great. Just remember that we have a next OCA meeting on July, which is next month, TBA. It's online. And then we have the beginners class on July 2nd online. And again, it's the first Friday of every month. So we'll see you there. Large events, that will be me as well. So right now they're still virtual. We have a lot of people that have reached out to us to do them fall, October, November. So we've been scheduling little by little to see how many of you volunteers actually are comfortable with going back on ground. So what we've been doing so far is scheduling virtual and then half and half hybrid. So we'll see how that works out. I know that maybe Chapman will be opening in a fall quarter, and most schools are opening in August and fall. So looking forward to having everything back on again and kind of normal. So. And now a moment with Galileo.
Hello, my name is Galileo. And yesterday was a full moon.
New
moon. And today is gonna be a waxing crescent. Bye.
All right, so moving on, we're gonna have the Serious Astronomer. If you want any items of interest that you feel like would be good to put in the newsletter, please contact Dave Fisher at the email there, and he'll review those items to be published. And then in addition, the Serious Astronomer is now available in an electronic format on the website. And then in the upcoming months, there will be information about being able to stop your paper subscription, go to online only if that's something that interests you. And then the trip to the Owens Valley Radio Observatory will be happening this year. It'll be at the end of July, Saturday, July 31st. Doug, did you want to say anything about this?
Yeah, I just got word this week that the OVRO site will be opened up and no restrictions except anybody that's not inoculated or vaccinated needs to wear a mask. But otherwise, it'll be open and we'll have a regular tour and the usual people, I hope, and I hope everybody can come.
All right. So now at the ANSYS site, we still have the same rules right now as the club can't be responsible for anything that happens there. discouraging particularly large groups from visiting, as it says, members and groups are still not allowed this time. If you do go out on your own, you're doing that at your own risk, as the club cannot sanitize the facility and meet other COVID guidelines. And then also, if you are going out there, please help in clear weeds, especially for those who may still not be comfortable going out there to do this maintenance. So please do help in maintain the common areas and then your pad and observatory areas. And then the next online meeting will be July 9th for the general meeting. And I'll turn it over now to John Garrett for the What's Up presentation.
I always learn a lot by doing these and preparing them. I thought I'd share a little photograph of my observatory. I have a balcony observatory that doubles as a seismograph, and I've been leaving my scope set up for several weeks at a time. That's one of the advantages of this whole era of the lockdown, that I've actually gotten time to learn how to use my scope properly. But this is what I do all my photography with the exception of wide field images, which I do take a lot just standing on a tripod and with a simple mount. Anyway, I'll start with some items that are in the morning sky. And so earlier this week, I went out and took yet another photograph of my neighbor's home at 5 o'clock in the morning. He hasn't wondered why I do that so often, but this shows the view of a late crescent moon at the beginning of this week. And by splicing two photographs together, I can give you an approximate view of where to find the brightest planets right now. And the two brightest objects in that second picture I just showed is Jupiter and Saturn. And Saturn is over in the constellation Capricornus. And there it is. Jupiter is right here, the brightest one. It's hard to miss. But the basic message is that the two brightest planets are together in the morning sky, and you need to get up, 4:30 to observe them. You can get up earlier, of course, and observe them. But the disadvantage is that it's pretty early in the morning, but at least you get two good planets to view. So they're coming back into view. This is my approximation of where the ecliptic plane would be. That is the path that the planets generally follow, and this the path that the sun follows. And my guess is that Neptune is about right there, just missed by my photos. But if you do get up for a morning planet session, you've got 3 planets to look for, all about evenly spaced in the morning sky. Another object that I've been following is a nova in Cassiopeia, very close to the Messier object M52. And I found that if I just point my telescope at M52 and photograph, I've been able to capture and track the progress of this nova over the past 3 months. And so here's a little rendition of how the major constellations appear at about 4:30 in the morning. And right near Cassiopeia on the right, you will see a little red star, and that's about where M52 is. So that's where you need to look to see this ongoing nova. And here is the field of view in my small 3-inch refractor that I showed you at the beginning of this presentation. That was on the top of my scope. And this shows a M52 on the right and where the nova appeared. So by the March 19th, here was the nova. And then 1 month later, the nova continued to appear about the same brightness. But here's where it got interesting. About after 3 months is when I was expecting the nova to noticeably dim. And I'd been trying to get up and get photos in the morning sky of it, but 2 things keep interfering, is that we've had a lot of marine layers and I don't always wake up every morning. But when those 2 cycles matched up perfectly, I was able to get up on the morning of the 9th of May, and the nova had just brightened that previous night. So I was able to capture it on the first morning of brightness. And so, so we go from 418, now 2 months after the nova first appeared, suddenly, almost 2 months, it suddenly brightens again, which I think is very interesting. So that makes it, at least for me, very interesting to continue to track throughout these mornings. I did check on it in June, and it's about the same brightness as it was before it brightened a second time. And just this morning, it's holding steady, but it's worth looking at. So those are some good things to see in the morning sky. If you set up and can find M52, you should be able to photograph or observe the nova. Now let's look at the evening sky. Yeah, this is a view from my balcony observatory, a wide field view, and I hope you can see Saturn down low between the trees there. I mean, not Saturn, Venus down low between the trees. And so I've circled it there and labeled it so I don't forget to call it Venus. And then here's Castor and Pollux, the stars of Gemini, up a little higher. And in this field of view, Mars is somewhere in this tree. And tomorrow, June 12th, the crescent moon is going to be about 1.5 degrees from Venus. So that would be a good thing to get together in a pair of binoculars or a telescope. And then the next day, June 13th, it's going to be very close to Mars. And then it's going to move on through the sky. But over this time, over the next month, Venus is going to travel, I estimate, about that far in the sky. And Mars, too, is going to travel, but it's got a little head start. But Venus is trying to catch up from our parent view with Mars. Now here's a photo I took a couple nights later, hoping to get all of the planets, that is Mars and Venus, but it was cloudy and I had forgotten an important piece of equipment, so I couldn't center my camera correctly. But here is the stars, Castor, Pollux, and Mars, same as the ones just seen in the previous view. And in this picture, you can also see the faint constellation Cancer, the crab, and Cancer is most notable for having the beehive star cluster, which is a very pleasant view in binoculars and at low power in a telescope. But by the 22nd, Mars is actually going to move into that cluster. So that will also make a very nice opportunity to see them together. And then by the 30th, Mars will have exited that cluster, but Venus is starting to move into it. So you're going to get another view of the cluster with Venus in it early next month. And you might have noticed a little flare off to the side. I thought I'd highlight that accident. Now that there's a lot of talk about UFOs with new government documents being released, I'm actually being asked to include commentary on UFOs in my presentations. And I'm kind of coming up blank because as a general rule, amateur astronomers who spend a lot of time looking at and photographing the skies don't seem to be reporting very many unidentified flying objects. But it might be kind of fun to go through our films and capture everything that ever looked strange. And so here's one of them, and we can show that a lot of them usually just come out to have normal explanations. But it turns out that this was a real object and not me accidentally drawing on my film. And I live near an airport where the military does regular night skydives, and they usually use white flares when they come down. But I do believe that this is a parachuter in using a red flare as they come down. And I then checked my other photographs that I took that same night, the ones that are before and after this one, and I see many more of these things in the pictures, suggesting the trickle down of parachutists, which I often see during the day. But it made for a very interesting puzzle to consider. And another example that so many things that you see in the sky that are really strange, if you give a moment to capture them, they turn out to have very normal explanations. I photographed the moon with my larger telescope, the 8-inch Schmidt-Cassegrain, so I could do a comparison with how big the planets Venus and Mars will look right now. And so here is Mars photographed with the exact same equipment as I photographed the moon. And you can see that that Mars is actually a very small target. So it's not really a great object to expect a good view of the planet because it's so far away, but it's really a nice object to see in the composition of some of the star clusters that it passes through. But I estimate that Mars should appear in a telescope about the size of that little crater on the moon, how that would appear. And same with Venus. Venus is pretty low, and I wasn't able to get a clean shot of it, but you can appreciate that if my photo wasn't so blurry because of the atmospheric distortion, that Venus would also be a very small object, no bigger than that crater as viewed right now. Now, Mars is going to continue to get smaller, but Venus is going to get closer and closer to us over the next few months. And just because I stuck whiskers in it because I think my picture started to look a lot like a mouse, so I might as well just run with it. Now, if we look at the deep sky objects that don't move very often, and when they do, it's very interesting. I walked out into my driveway this week and took a wide field shot of the sky toward the west, but looking up very high. And you can see the constellation Leo the Lion, its characteristic sickle shape. Leo is starting his nosedive into the west, but it's still a good time to capture some interesting objects in Leo that are fairly bright and fairly easy to find, especially if you go to a dark location like where I took this picture. And so here's Leo the Lion, and here's the bright stars labeled in the constellation traced, Nebula over where its tail is, and Regulus. And if you draw a line between those, that line passes very close to some fairly bright Messier objects, which are galaxies. And here's a trio of M65, M66. That's the one that you see right here. And this was taken with my 3-inch telescope at a fairly dark site. And also the galaxy NGC 3628. And then here's M95 and M96 and M105. And I actually am not sure which is which, but that's part of the reason I share this stuff so that you can have a look yourself and make that discovery too. Anyway, one thing else I was noticing, and this will appeal only to Star Trek fans, but while I was looking at the star chart to identify these objects, I discovered that the famous star Wolf 359, where a battle is going to take place in the 24th century, a battle for the fate of Earth, actually is in Leo. So while Leo's still up, here's your chance to hunt down Wolf 359. And these other numbered stars are just numbered stars in Leo that I used to eliminate as I tried to find which one in my picture was actually Wolf 359. It shows up in a 3-minute wide field photograph taken from a dark site. Also back to my driveway, I flip a little farther to the north with my camera, and then here's the Big Dipper, or Ursa Major, which is actually high overhead. My camera is on a small equatorial mount, so it doesn't actually align easily with the horizon. So you have to look at the house and follow a line there to appreciate that this is actually pointed straight this way, and I'm looking up fairly high, which makes it a very good time to see some of the objects that are in the Big Dipper before it fades off into the west. And so some of those are M97, the Owl Nebula, a planetary nebula, M108, an edge-on galaxy. Those edge-on galaxies, I think, are one of the most interesting things, because when you start staring at them and you actually start to see them, and then you can kind of see the dust lanes or anything in that, it gets pretty exciting. And then M51 and M101 are up by the tail, the handle of the Big Dipper. And here's a photo I took with my 3-inch telescope of the Owl Nebula and M108. This was at a dark location. And here's the same couple taken from my backyard balcony observatory. So you can appreciate a little bit of the difference in sky, but it's still not too bad. You can take a 3-inch telescope, you can have it stare at the sky for about a minute, and you can pull in these objects. And I don't really spend a lot of time trying to get great photos. There's a lot of people doing that and doing incredible work. I'm just finding fun using my camera as sort of an assistant to help me observe something and find where it is, even from my backyard. And also, this was actually taken from my backyard this week with my 3-inch telescope, and it shows you how much clearer the sky gets as you go across the length of the Big Dipper. So this one here is toward the bottom, lower part of the Big Dipper at this time of year. Then you go up maybe 15 degrees. I'm not sure, I don't recall how far that is. And the sky actually gets noticeably brighter so that you can pull out something like M51 with a 1 minute exposure. And this is a beautiful galaxy. It has like this 2 pairs of galaxies. The another object which I mentioned was M101. This was taken, this one also has the better conditions because it's near M51, but I had to tweak the photograph more to bring it out enough so that you can see it. But still, I'm pretty excited at being able to do that. But one of the things is that pixels do get harmed by my processing. I definitely take a picture and I'll try to tweak it in Photoshop just to try to detect what's in that picture. And so anyway, the Big Dipper, and near the Big Dipper's handle, recently I've become fascinated with carbon stars, and these are stars that are near the end of their life. They're variable stars, they're pulsating, and they've also accumulated a lot of carbon in their atmospheres, giving them a very red color. And so there's one here that's been called La Superba, and it's a carbon star. And here's a photograph of it through my small refractor, very reddish, orangish, lovely color. But this is the first time I photographed it. And it does have, I think about maybe several months, it should change in brightness. So I actually look forward to discovering what that change is going to look like. And then while we're at it, every time I set up, I like to photograph whatever star I'm focusing on just to get my scope aligned. And it brings back that joy of just looking through a telescope and looking at a star and just enjoying something as simple as a star. The let's see, oh yeah, Big Dipper. Near the Big Dipper is also an open cluster, Coma Berenices, which stands for Bernice's hair, which is kind of a little feathery reference to just this star cluster that shows up very nice in binoculars. And also in this area, high overhead, there are 2 fairly good globular clusters. M53, I don't think gets enough attention because it's everyone knows about M3, they know about M13, they know about M5, but M53 is actually a nice one along with M3 in the same area. And so here's my picture of M53 taken just recently in the past 2 weeks from my balcony observatory with my small refractor. It's about a minute exposure. And here's M3 under the same photographing conditions. So a lot of things to see in the sky. It's also the shortest nights of the year now, but it's a good, but I mean, you have to wait a little longer for it to get dark, but there are plenty of nice things in the early evening, which is really what I focused on. The more I do these what's up, the more I recognize how many other stuff there is in the sky on any particular night, but we'll come to more of those as we do more of these what's up in the following months. So thank you.
Thank you, John. That was wonderful, great. We always learn a lot from your presentation and your all the original images that you share with us. Thank you very much. Hello, I am Reza, your Vice President, and I too would like to welcome you to the June 11th, 2021 General Meeting. Let me bring to your attention the ways in which you can interact with us during this meeting. First, please find and click on the raise hand button. This is how we're going to welcome our speakers shortly. Great, I'm seeing people trying that. Thank you. And second, chat. Use that to send us any comments you may have. Third is the Q&A option. Please use that to ask any questions you might have from our main speaker during and after the talk. And speaking of your questions, I should emphasize that the goal of our meetings is to promote astronomy to everyone. And hence, we encourage you to ask your questions without any inhibition. However, in order to keep the quality of our meetings, we do not handle questions verbatim. We combine, rephrase, and reorder them to fit the natural flow of the talk. So to get your answer, listen for the concept you asked about rather than your name or your words. Our speaker at this meeting is the director of the Kavli Institute for Theoretical Physics at UC Santa Barbara. Among his awards are the Alfred P. Sloan Foundation Fellowship, the Cottrell Scholar of the Research Corporation, the Helen B. Warner Prize from the American Astronomical Society, and the Danny Heinemann Prize for Astrophysics. He is a fellow of the American Association for the Advancement of Science, the American Physical Society, the American Astronomical Society, and was elected to the National Academy of Sciences in 2018. He is presently chair of the board of directors of both the Research Corporation for Science Advancement and the Las Cumbres Observatory. Please join me by raising your hand virtually in welcoming Dr. Lars Bulsten. Dr. Bulsten.
Thank you, Reza, and thank you all for coming this evening. I really welcome this opportunity to speak to all of you. I started my career in science by doing astronomical observations from Southern Ohio, 60 miles south of Columbus when I was quite young. And the major challenge at that time was when the sheriff would find you in the middle of the field in the middle of the night, they didn't quite believe that you were there to use an astronomical telescope. As you can only imagine, and many of you may have had that experience. So I really enjoyed your talk, John. I just caught the tail end of it, but reminded me of what brought me to science and what brings all of you here this evening. So I would like to go ahead and launch in. So Reza, am I good to start sharing? Okay, so let's see here. So hopefully this is visible to everyone. Reza, are we good?
Yes, we're all good, all ears.
Great. Okay, so what I'd like to do to this is give you a brief tour of what's been happening in our ability to really measure properties of stars all across our galaxy by really measuring their oscillations. So what I'm going to do this evening is walk through a little bit of physics on sound waves and then how we apply that understanding of sound waves to really unravel the properties of stars. So when I teach at UC Santa Barbara, I teach a graduate physics course called Stars with Lars. So you're going to get a little slice of that this evening. And I really do welcome questions. As I told Reza, I really do like to have the interaction. So follow whatever the protocols are, but please do feel free this evening to bring on questions. So this image is of the KITP where I usually work. This is Cone Hall right at the East Gate, for those of you who are familiar with the university in Santa Barbara. And this is where we have physicists and astronomers visiting all year round. Of course, the last 15 months, not the case. Typically 1,000 visitors a year come to the KITP and interact and start collaborations. That's our mission. And as director now for nearly 9 years, that's my goal, is to ensure that science keeps moving forward via collaborations. And many of the topics I'm going to talk about tonight have been impacted by people gathering together in this fine structure, which overlooks the Pacific Ocean. So I'm going to first start by what is a sound wave? So, you know, this is a pretty sophisticated group. And so I will hopefully tell you some things tonight you don't know, but I also always know that even when I go to a talk, it's nice to start off with something that maybe you're familiar with. So, you know, what is a sound wave? And of course, if I was giving this lecture in public with you, I'd be talking about the sound waves I'm sending to you. Right now, it's just a sound wave between me and my microphone. But when air is compressed, it basically pushes back due to a slight increase in pressure. And it does that just because as you compress any plasma or any gas, it gets a little bit hotter as you compress it. And that sets the restoring force. That's what makes it difficult to fully compress. And for air in this room or anywhere, I give you the number here, it's about 300 meters per second. Most of you probably know this. And of course, you also know that given that it's a finite travel time, you can use sound waves for triangulation. You can measure things by measuring time between no locations. Sound waves can provide a fair amount of information. And so you won't be surprised to hear that we're doing the same in stars. So again, this is sort of just to get you warmed up, just to understand what the sound wave is it's a alternating regions of compression and rarefaction with the typical wavelength, which we call lambda in physics. And the frequency of that wave is just given by the product of the the frequency is defined by the product of the wavelength and the frequency is the sound speed. The CS here is the sound speed that I had in this quantity. This is what I'm going to call CS. That's the sound speed of air. And so as you know, right, shorter wavelengths give you, of course, higher frequencies. And what I'm going to show you today is that stars show all of these properties. As we find oscillations in stars which have shorter wavelengths, namely many more nodes, much like in a musical instrument, the frequency goes up, no surprise. And as I'm going to show you, those measurements are happening, and they've been happening for about a decade due to space-based missions, CRO, Kepler, and now the TESS satellite. So it's a very exciting field. But before I go into stars, I want to give you a little bit of an unusual story that some of you may know, which is a slight digression, but it's an interesting digression because it's kind of fun, especially since we're all in California and the ocean is nearby. I want to talk briefly about how sound behaves in water. So this has absolutely nothing to do with stars, but it's just a cool story. And if you don't know it, I want to be certain you do. So I've given you the air case, which is going to be the case when we do stars. Okay, so this is just, I'm just adding a little piece here, which is completely unrelated to stars, but it's just really cool. So the speed of sound in water is very different. It's due to the fact that water is nearly incompressible. So it's very insensitive to temperature. And the speed is much higher. It's about 4 times faster than in air. And what I'm going to show you is, however, even though it's almost independent of temperature, there's a slight dependence on temperature. And water that's near the surface of the ocean, right outside where you are and where I am, especially near the equator, is a little bit hotter. And so the sound speed increases slightly near the surface because it is a little bit hotter. And then as you go down, it increases again due to the fact that it's a higher pressure. As all of you know, if you go down about 30 feet, 10 meters, the pressure doubles. Very little compression, but the pressure goes up. And as you go deep in the ocean, this is what the sound speed looks like. So this is an old school plot from oceanography books. So it's a little bit of an unusual plot. The x-axis here is showing the sound velocity, and they're using units I hate, but we have to live with it, feet per second. So just to orient yourself, this is depth in thousands of feet. So going down is here, and the surface of the ocean is here. They're showing the profile of the sound speed. So let's go to latitude 19 degrees north. The sound speed is high at the surface because the water's hot. As you go down into the ocean in this direction, the sound speed declines. And then it rises again as you go deep in because of the pressure rise. And if you go to northern latitudes, it's not nearly as hot at the surface. So this effect of seeing the increase in the sound speed is very slight. Okay. Well, it ends up, if you have a profile of the sound speed that looks like this, you can get a very interesting bit of phenomenology in the Earth's ocean. And that has to do with how a sound wave propagates. So many of you are building telescopes, probably. Many of you may use lenses. And so you're familiar with Snell's law. I would ask you to, if I was in the crowd, I'd say, raise your hand if you've heard Snell's law. So raise your hand if you've heard Snell's law. Come on, somebody. Uh-oh. You can just raise your hand. Yeah, you can just do it this way.
Yeah, we have at least tens of people in the audience raising their hands. Yeah.
Okay. So what happens as the sound wave goes down, as the sound speed is rising, and the ray gets bent. Okay. And this is one reason. So as you're in the ocean, as you're going deeper into the ocean, the ray will get bent, just like in normal optics. And this is going to be relevant for stars. So this part is going to be relevant when we do stars in a minute. Okay. And so what this means is the following. And so I'm going to show this plot. It's very busy. So just take a breath, but it's going to be a great plot. So again, this is from an old school figure. So it's a very simple plot. It's depth going down. And now it's in maritime units of a fathom. Now you're all astronomers, so you're accustomed to using weird units, so you shouldn't be scared. but you've probably never used a fathom to describe anything unless you're someone who spends time on the water. And what they're showing here is if I take a point explosion down in the ocean at this depth, and I send out rays in all directions, okay? The ray that goes off at 15.19 degrees from here will go up to the surface, it will bounce, it will come down. So across in this direction is range, distance from the explosion, goes down, turns, it gets steered away because as it goes down deeper in the water, the sound speed's rising, it gets steered up and goes here. A ray that's only at 2 degrees, so it's nearly in the plane, okay? Nearly in the plane, almost perpendicular to gravity, gets very quickly deflected and travels in a very narrow channel. Now, this might seem very esoteric, but this was discovered in the 40s with the remarkable experiment by Ewing, who was an oceanographer, who took a few pounds of TNT off the coast of Africa and detected in the Bahamas the sound waves arriving. And the reason for that is that the rays that went in parallel, they spread, but they stay in a very narrow channel. So it's not diffusing like 1 over r squared. It's not spherical loss of energy. It's just the planar loss of spreading in a plane. So the amplitude stays very high because everything's focused in this channel. And this channel is still being used actively as a way to measure the ocean temperatures. So the other reason it's of interest is that this is called the SOFAR channel. And you can use this, and it has been used for basically studying and monitoring the change in the temperature of the Earth's oceans. Because you can imagine if they heat up or cool, all this physics is different, right? These sound speeds change. So how many of you knew about the SOFAR channel in the ocean? Reza, you got to give me a head count while I drink my water.
Sure, I'm waiting for people to raise their hands. So far, one person has indicated that they knew about this.
Okay, great. I figured the only way to tell this crowd anything is to talk about anything but stars. So far, I'm right.
Right, 3 people. Okay.
3 people. Okay. So now, this is a beautiful snapshot from Popular Mechanics in 1949, talking about the then finally released use of the SOFAR channel for finding downed pilots during World War II. So downed pilots had a small detonation charge. They were told when they were in the water to drop the charge. It was a depth charge. It would float down to the depth where this channel resides, the minimum in the sound speed. They would probably be told at what latitude. I think it had a latitude. There was something, I'm not sure. It would set off a detonation. And then there were sound detectors in, here's Point Sur, here's Point Arena, here's something in Hawaii. And then by triangulation of the arrival times from 3 different sites, you could figure out roughly where the downed pilot was, and you could send somebody to maybe pull them out of the water. Okay, so this is super crazy cool. I just thought I would share this with all of you. 1949. Okay.
Okay, so since you mentioned it's okay to interrupt you,
yes.
Can I check if I got a correct understanding of the phenomena?
Sure.
So because of the variation in the sound speed in water, we're going to have total reflection at certain depths. So a phenomena similar to what happens in optical lines happens with light, with sound waves, and they do not spread as much. They just get reflected in a narrow band, and that has some practical usages. Am I correct?
You are correct. And it's this, that's why I went back to this slide. It's because the speed goes up again at the surface. This does not happen in stars. Well, there's a few stars where you can get this weird inversion, but I'm not going to talk about that this evening. I've been searching for this in stars. So it would just be fun as a historical story, but you understood it correctly.
Excellent. Thank you.
So the reason I wanted to tell that story is to sort of set the stage for, and we're going to do stars now. When you go into a star, the temperature gets higher, sound speed goes up, of course, right? Okay, so now let's do the star. So very simply, if you want to understand a star, the what we call hydrostatic balance is the fact that the way a star functions, independent of any energy source, this is not having anything to do with fusion. The way a star works is you have a finite mass of material, M, and a radius R. If you give me that, I can calculate the pressure at the center just from hydrostatic pressure, right? Just like you go down in water, the pressure rises. So I can calculate the pressure at the center. For the star to be in hydrostatic equilibrium, it has to have an ideal gas pressure to push back to balance that hydrostatic pressure. That algebra gives you this relationship I've shown, this first equation, which is the Boltzmann constant times the central temperature equals the gravitational constant, the mass of the star. This is the mass of a proton. I'm assuming it's just pure hydrogen for now, and the radius R. So this is a relationship that says the average thermal energy of a particle in a star, deep in the star, not at the surface, deep in the star, is equal to the average gravitational potential energy. That's probably a familiar formula. This formula may be familiar to you. So that's the temperature of the center. Of course, there's a gradient in temperature as you go out to the surface because it's hot at the center, it's cold at the surface. Vacuum is 0 officially. And then it's a heat transfer problem, right? I've got a hot center. I have a certain amount of stuff I have to diffuse through. That roughly gives you an R value if you want to think of it as insulation. That R value tells you how much heat is coming out of the star. That's what we call the luminosity of the star. That's what sets the luminosity. And the surface temperature is just set by the fact that you have to have 4 pi r squared sigma t to the 4th equals a luminosity that gives me the surface temperature. So that's it. So basically you've done now all of stars, okay? Everything else is a detail. Now we're going to do sound waves. So what we really want to start to get an intuition for is how long does it take for a sound wave to cross the whole star, okay? Because we're going to be looking at stars in the end halfway across the galaxy. So we're not going to see little wavelengths. We're going to need to see the big oscillations, the ones that have big waves going all around. So that's roughly going to be the radius over the sound speed. If I have the temperature, this KT, I can calculate the sound speed. And I use this formula to get that, and I get a crossing time for a sound wave to cross the star, which the formula is this, which is the radius cubed divided by GM. The M over R cubed is the mean density, right? So for the sun, the mean density of the sun, gram per cc, it's the same as water. That's the mean density of the sun. Okay, so this is a few hours. If you just put the numbers in for the sun, this is a few hours for the sun. So the time it takes a sound wave to go around, or the time it would take to go through the center is a few hours. This also makes clear, is what I'm going to talk about for most of the data I'm going to show after I've explained what we learned from the sun, is that as the radius grows, when stars become red giants, same mass star, this time gets very long, right? So as the star grows, this time scale, the crossing time for a sound wave, gets very long, days to weeks for giants, red giants. Okay, so you've done stellar physics now. We're not going to worry about the energy source. It doesn't matter. It's just a hydrostatic ball as far as we're concerned. All right, so let's do the sun. Now, again, most of you probably don't observe the sun. That's probably for the better. But, we have one. Okay, good, excellent. So the sun is a beautiful thing for stellar physicists because you can really resolve small scale structure, right? And in no other star can we do that. So we're kind of spoiled. Doug has a question.
Yeah, no, I'm going to make a statement. We have a 60 kilohertz solar radio telescope at home for the last 20 years. We observe coronal mass ejections, and we have a hydrogen alpha telescope we've used for lots of eclipses. And I think there probably are half a dozen to a dozen other OCAs that have hydrogen alpha telescopes. And we have just last week a neutral hydrogen observatory using a 6-foot dish.
Awesome. That's great. Thank you. Thank you, Doug. So, yeah, no, it's great. So what happened in the sun? I'm really just going to tell the story about oscillations in the sun. That's all I'm really going to highlight here, because that's what I need to do. So in the early 60s, it was discovered that there were persistent oscillations of the sun with a period of a few minutes, 5 minutes. And these were all being studied by Doppler Shift measurements. So taking spectra of the sun in patches or in large regions, and noticing the Doppler shift. If you just take the velocities of lines and you measure the Doppler shift, that's how all these measurements were made. they were very coherent. They were moving at about this sort of 0.5 kilometer per second number I'm giving you here. And it took a while, but in the end, what was understood was that if you look at the sun, of course, the core is where the hydrogen fusion is occurring, from all the way to the center up to this region, roughly this fraction of the star, is very quiescent. There's pretty much nothing going on. There's no convection. And then there's the outer convection zone, which makes the sun a very exciting thing to witness. And what became understood over time was that the convection zone and this broiling motion of the convection ends up over time, if you let it sit and bubble and boil, have the ringing mode oscillations of the star get to a finite amplitude. Okay, so these oscillations, they're normal mode oscillations, so it's not totally the same, but it's not unlike your car, which might have a resonance at a certain speed or something where it really rattles. And stars have normal modes of oscillations. It's the frequencies these things like to ring at. And these what we call normal modes of oscillation, end up getting to a finite amplitude, and we can observe them. And so it ends up being like a musical instrument with many possible tones. And in the sun, because it's close, you can observe small patches and really see small wavelength perturbations, okay? And so for the sun, there's a tremendous story to be told, which I'm not going to tell this evening, of everything you can learn about the sun, because we can't do much of that for other stars, okay? So it's sort of not as rich for other stars as it is for the sun. But it does have many possible tones, and I'm going to show you that a little bit. But let me now go back and show you a little bit of ray tracing in a generic star, which builds on what I talked about before for the Earth's ocean. So what's shown here are different rays with different incident penetrating angles. And you can see that something like this blue line, which is a nearly radial ray, can get quite deep before it gets deflected to come back out. Whereas something like the green ray, which is coming at a more acute, not right radial, but has some offset, will deflect at a larger radius. And so if you really want to get things that penetrate to the core of the sun, you need to see the wavelengths which have a wavelength of order the sun. So in spherical harmonics, it's a dipole oscillation or a quadrupole oscillation. So I'm going to use little l. L of 1 is a dipole, L of 2 is quadrupole, L of 0 is a radial mode when we do distant stars. So I will be using these spherical harmonics, which you can really just think of as what's the wavelength of the wave relative to the size of the star, right? And so for something far, far away, you're not going to be able to see some disturbance due to this red curve. It's just not going to show up. It's going to get canceled because of the integration over the surface of the star. So for the sun, all of the work was done. You ask, what were the measurements? The measurements were indeed Doppler shifts of the velocities of surface elements, okay? So those were the measurements. So those measurements were able to do many, many things. So let me show you a few highlights for the sun. So you can map out by looking at these different waves, some that penetrate deeper than others, and seeing that those that penetrate deeper get to measure the sound speed in a different place. You can actually invert that and measure, this is the sound speed squared, but the sound speed of the sun from the center, this is the center of the sun, to the surface, and actually infer the changing sound speed. Now, if you may be a little curious, like why is the sound speed going down at the center? I mean, this is the measurement. This is true, right? I told you at the beginning that the temperature has to be monotonic. It has to be increasing towards the center, right? Because it's hot at the center and cold at the edge. So anybody have any idea why the sound speed would drop as they get near the center of the sun? I'm going to pause. This is a quiz for the crowd.
Density?
Density is monotonic. It's getting denser and denser as you go in.
So the audience can use the chat to send in their response to the question on why.
Sorry, Reza, if I'm challenging the scene here.
No, that's actually something we appreciate. Yeah, getting the audience participation. So if you can again say your question one more time, just
yeah. So what I'm highlighting here, here's the surface of the sun, and this is the sound speed squared. So don't worry about that. But it's the sound speed. So as you go in, it gets higher and higher and higher. And the sound speed should go like the square root of the temperature, right? And suddenly, As you get very near the center, the sound speed drops, but the temperature is climbing. It has to be. What's happening at the center of the sun? We're fusing. We're fusing hydrogen to helium. So what's different about the center of the sun at this place than out here is there's more helium here and less hydrogen. So for those of you who've entertained yourself or your family or your students by inhaling helium and speaking, right? That's the sound speed knows about the composition, okay? The sound speed knows the composition of the material. And so this decrement in the sound speed is because of the fact that the center of the sun has less hydrogen and more helium. And that brings down the sound speed. So in this case, helium is heavier than hydrogen, right? In this case. So really remarkable. I mean, this is quite astonishing ability using acoustic waves in the sun.
Okay. And before we go ahead, we have two questions. One of them is that, can you explain more about the mechanism that gives rise to these 5-minute solar oscillations?
Yeah, I will do a little bit more on that in a little bit. So there's more coming. Yeah. So ask that one. If I don't address it, please ask again, Reza.
And the other question concerns the Doppler shift that you mentioned is used to measure these. Somebody needs more explanation because their idea is that Doppler shift is used for things that are moving away or towards us. So what is moving here?
That's great. Great question. So if I'm staring at the sun, so let's say I'm staring at one of these patches, as the wave goes by, just as in an ocean wave, it moves up and it moves down, right? So if you're looking down at the ocean, the water moves up for a period and it moves down for the period. So you're right, it's the motion coming at us or going away that is the Doppler measurement that's made.
And speaking of waves, how deep and how high do they go? Do we have an exact measurement for that?
Yes. So for the sun, if you look at what we call low L, little l is the spherical harmonic. Low L are very long wavelength, like the blue or the green. They go all the way into the center. So these waves are very deeply penetrating. And the waves I'm going to talk about in red giants are the same. So they're going all through the star.
Excellent. And we do have a question about, since you mentioned the reason for the change in velocity near the center is we're going to have higher concentration of helium there. What happens to this velocity when the star starts fusing carbon?
Yeah, so as a star ages, and it burns more and more fuel. If I go back to this equation, what I haven't told you is, why does the sun have the temperature it does? I haven't derived the temperature for you. I haven't derived the radius. This is a relationship, but I haven't given you this. Well, the way it works in a sun is, as I said, it's losing heat because it's hot at the center and cold at the edge. That gives me a luminosity, which I can calculate. What happens in any star, all stars, is it will continue to contract until the temperature is hot enough, this KT is hot enough, that the fusion reactions match the luminosity leaving. And then the star says, I'm happy, I'm here as long as I have fuel. And that's what it does. And the sun's halfway done-ish. Then when it runs out of fuel, it has to burn the next thing. To burn the next thing, it has to be even hotter because the cool penetration factor is a penalty as you try to burn that has more charge. The star has to get, at the core, the star gets smaller and smaller. So if I'm living under the star, this temperature is constantly rising with time. And so the sound speed, if I'm living at the center of a star, is constantly rising. Okay, are we good, Reza?
Yes, we're all good.
Okay, so the other thing measured in the sun was rotation. So some waves go in one direction, some waves go in the other direction. You can actually measure the rotation of the sun. Quite remarkable. And of course, all of you know at the surface of the sun, there's differential rotation with these are different latitudes. And so the sun shows latitudinal variation. This dashed line is the convection zone. So from here to here is fully convective. And then this is the part of the star I was describing as sort of quiet, no convection going on. This is the measurement that shows the center of the sun is rigidly rotating with a rotation rate of about 27 days. Quite remarkable. Okay, so that's the sun. That's exciting. Sun's I got one. What I want to do in the rest of my talk is talk about the thousands of stars across the galaxy for which the astronomical community has made tremendous progress. Not this detailed, because this is pretty hard, but quite remarkable. So I don't need to show an image like this to this crowd. Everybody knows this constellation. So let's talk about distant stars. So what's the problem? The problem with a star far away is this is just showing the perturbation of temperature at the surface of the star. So this L is the spherical harmonic, M is the angular harmonic. But you can imagine if something like this is happening, this, and it's time dependent, the brightness of the star will change a little bit, okay? But if I had a lot of waves going around, this plus minus, plus minus, plus minus, plus minus cancels out. And so for distant stars, we're not going to get to see waves like this. We're going to be stuck seeing low L waves. Okay, that's all we're going to get. Now, the advantage, as I said, of those is they do go deep into the star. So they do provide great probes, but it limits how much we can get. Okay. Okay, so what I'm going to do is now say, well, what would the sun look like if we integrated over the whole stellar disk of the sun, right? So we put a satellite far away, we just stare at the sun, make it a point source. What would the sun look like? Well, you don't get millions of modes anymore. You get this. So if you just take the power spectral density, and I'll explain what that is in a moment, of the radial velocity amplitudes of all of these perturbations. So this is showing the Fourier transform. Basically, this is the frequency of the oscillations. And this is how much power, how much amplitude, how variable the star is at these frequencies is what this measure is, which is all you really need to see. You don't see a lot of stuff, but you do see. Here's the 5 minutes. So this is the actual, what you would see. This is the 5 minutes. These are typically L of 0 or 1 or 2. The formula is very simple. It's a musical instrument. So if N is the number of radial nodes in the wave, okay, how many, as it goes in, how many oscillations does it have? That's N. L is the angular, this epsilon you can ignore for this talk. So these things are frequency, uniformly spaced in frequency. It's a musical instrument. If I add one more node, I will double the frequency, okay? And that's what you see. You can see the uniform spacing. It's sort of very evident here. This uniform spacing is just related to the sound speed and how long it takes to get to the center. So this frequency, 1 over this frequency, which is a time scale, is just the travel time to get to the center of the star. So it's like what I said, it takes the measurements, the modes, know about the time it takes to get to the center of the star. And because of that, and because of the fact the star is in hydrostatic balance, I can use the measured frequency spacing, this delta nu, and infer the mean density. Okay, that's what I can do. So if I can measure this frequency spacing and I can do a little bit of theory, I can get the prefactor right, and I can actually measure the mean density of the star. Okay, so that's pretty remarkable to think about. So if you ask what properties of stars can you measure, right? You're very accustomed to measuring, if you know the distance, the luminosity. If you can get a spectrum, you can get the temperature. But now I'm showing you that if I can see these waves and I can measure this frequency spacing, I will actually measure the mean density. So I'll be measuring a quantity which is the mass divided by the cube of the radius. And obviously this has happened, otherwise I wouldn't be giving this talk, right? Now, I'm going to show you different stars, and I'm going to say it for giants. For the sun, I don't remember right now, but it's a fair question to ask. Well, what N is this? What N is that? Obviously, as I'm going to the right, the frequency is going up. So I'm getting more and more radial nodes, okay? So the frequency is going up to the right as I go this direction. So what is N? I don't know for the sun. I'll show you cases of giants where I know this better. Doesn't really matter. You see, as I go up to high N, suddenly there's nothing going on. There's no power. There's no variability. For some reason, the high frequency waves aren't getting to high amplitude. And that's the other piece of physics we have to explain, and then we can go off and have fun. So if I look at the sun, and I now go to not a linear plot of the amount of power, just think of this amount of variability. How loud is it? If it were brightness, it would be how noisy is it? This is sort of how loud it is if you're sitting on the star. And I go up, this is all of those little spikes I saw, but it's now sort of compressed. But as I go to higher frequencies, there's nothing happening. The star gets very quiet. That's this decline I'm seeing. So we have to understand why that is. So let me just tell you this physics. I'm not going to read this slide in detail. But what's happening is, as the wave gets near the surface, the sound speed, because the temperature is dropping, the sound speed really drops, right? The sound speed drops dramatically. And what that means is, for the wave to keep a constant frequency, it has to become shorter and shorter in its distance over which it's changing its properties. And you can think of this as the wave is trying to see, is the boundary a reflective boundary, or is it something that's going to transmit and leak out? And so the wavelength of the wave at that location tells you, relative to the distance over which density is changing, which we call the scale height, that tells you whether or not the boundary condition of the wave, reflecting boundary condition or a leaky boundary condition. As you go to high frequencies and the wavelengths are getting shorter and shorter, this surface becomes very leaky. And if it's very leaky, then the wave is stamped, doesn't get to high amplitude. That's the physics. And that ends up, what that knows about is the distance scale, what we call the scale height. So in any star, at any location, there's a distance you can move vertically, where as I go up that distance, the density is down by 1 exponential e-fold. For the Earth's atmosphere, this is about 30,000 feet. There's a reason planes fly. Well, it's a different reason, but it's about 30,000 feet. Okay, so if we go up to 30,000 feet, the density is about 1/3 that of atmospheric pressure. And so that's a characteristic length scale. Obviously, that length scale, if I have higher gravity, gets shorter and shorter and shorter. And so by measuring that length scale, I actually measure gravity for the star. So by seeing the fact that there's no waves up here, there's a way, using theoretical understanding and a fair amount of empirical inference, to take this high frequency that's seen, or you can go to this plot, just say, well, it's roughly here, everything else dies off. That free measurement allows you, in concert with knowing the surface temperature, to measure the scale height at the surface of the star. And if I know the scale height, I can tell you what gravity is at the surface. Okay? And so now what I'm saying is, by measuring 2 numbers, the frequency spacing, this number, and a frequency above which there's almost no power, this number, I now have measured the mass and the radius of the star. Because I have m over r squared here, and I have m over r cubed here, and I'm done. Right? 2 measurements I've seen for the star, and 2 unknowns, the mass and the radius. So now when you do this for the sun, this is pretty boring. We know the mass of the sun, we know the radius of the sun, so it's not that exciting. But if you can do this for thousands of stars across the galaxy, now you have something worth talking about. And that's what I'm going to highlight for the rest of the talk. So let me pause there, because that was a fair amount of content. So let me pause and see if there's questions, Reza.
Is that millihertz or megahertz?
This is millihertz.
Okay. And the previous graph was microhertz?
Yep, that's what they love to do to you to make it hard. So 3,000 microhertz, let's check. Hopefully 3 millihertz, yep. Yep, you got it right, Doug.
Okay, and we have a question if these waves on the surface of the sun are related to corona mass ejections.
They definitely, waves get excited by all the stellar surface activity. So you can do, so the best case I know of something, it doesn't, so the answer is the waves get excited, yes. You can see solar flares or coronal mass ejections on the backside of the sun because of the sound waves come around. So there is a way to actually monitor the backside of the sun by looking in detail for the acoustic waves that are excited by something happening over there, because it doesn't come around. So an hour later, the signal's here, or I mean on the visible side.
I'm sorry to interrupt. Doesn't the Gong satellite give us that information?
Yeah, there's many satellites. I haven't really been that good at highlighting the tremendous number of ground-based and space-based instruments for the sun. But yeah, I mean, yeah, it's not really a field I'm deeply involved in, so I'm not certainly highlighting all the instruments that are making these measurements.
In looking at the sun at different frequencies, there's several websites and it'll show a dozen different telescopes. One of them is the Gong telescope, and it does show the echogram of the sun and what's on the far side. That's one way of, at least a while ago, of inferring what was out of our visual frame of reference. But I'd encourage anybody who's interested in that to go and look around a little bit. It's amazing. It's just amazing. The acoustical aspect of the thing is amazing. Thank you.
Yeah.
And you, on one of your slides, you did have a thing about the solar neutrino problem, and somebody's asking, how do these measurements help resolve that?
Yeah, so that measurement I showed you of the sound speed of the sun has, once you've made that measurement and you've done the stellar evolution, you have a very, very secure prediction for the neutrino output of the sun. That prediction was true, but it wasn't what was being measured. And that was the solar neutrino problem, which of course got solved by the physics realization that neutrinos change flavor. So this is a rare case, I would say, of an astrophysical understanding so deep that we were able to reveal new physics. This is not usually what happens. I always tell students that's a fine ambition, but it's not the high probability success. But in the sun, it worked.
Okay, excellent. And just to make sure, again, an understanding check. So all these, what you said basically is that all the stars have these vibrations, and we are able to observe a specific frequency of these observations from distant stars. And from those, because of the relation they have with the density and then gravitation, we are basically indirectly capable to induce the gravity at the surface of these stars. Am I right?
That's right. Yeah, and I'm going to show that now. Yep, I'm going to explain that in more detail. Yep.
Yeah, you're going to tell us about more detail, okay? Because we still have, again, the same question asked again about what is the origin of these waves, or what's the mechanism? Yeah, we'll wait for that.
Okay, great. So let me show you a little bit of the infamous HR diagram. So this is showing stellar evolution for different mass stars. This is from the open source code MESA that we've been developing for over a decade now. It's an available code. So any of you want to run stellar evolution, just Google modules, experiments in stellar astrophysics. We've got about 1,000 users now, and it's available on the web. You can download and run it and really do stellar evolution, or you can actually access it another way. So please go look at that. What's shown here is something like the sun. Everything I've been talking about is the sun sitting here at 1, of course, in solar units. But as you know, when the star runs out of burning hydrogen in its center and the helium core contracts, the envelope expands and it really becomes quite bright. It becomes what we call a red giant, all the way up to about 1,000 times brighter than the sun. Okay. So these are the stars I'm going to talk about. The reason we can talk about them is because of these 2 satellites, plus now the test satellite, which were launched. These are now over a decade old. The Corot satellite was a French satellite, 27 centimeter diameter into space, launched back then. Kepler, many of you have heard about, I'm sure, 95 centimeter diameter, launched and now no longer functioning, 2009. Now, both of these instruments were used as well, measuring for finding planets around nearby stars, right? Look, transits. So that's their prime use. I would argue their prime use has been what I'm going to tell you now. So you thought you probably knew why they were built, but they were really built to do stellar astrophysics and astroseismology from my perspective. Now, I don't have to tell you the advantage of going into space, but it's basically you're getting data that's at Poisson counting. And so you can measure the brightness variations of stars to a much more delicate level than you can do from the ground, right? So from the ground, typically you can't better than about 1% photometry, 10 millimags in your units. You're going to see things here that are micromags. Okay, and so part in 10 to the 6 part per million is what we tend to use as our unit. And it's just because the variance is just Poisson limiting based on the number of photons you get. So why giants? Well, so here's our red giant. Here's a schematic of a red giant. I've got a helium core, which is pretty quiet and boring for most of the case. But then I've got this huge envelope, which is the whole thing is convecting. So the volume of the star, the most of the volume of the star is convecting, bubbling, and broiling away. And it's much brighter. So it's trying to carry heat much more than in the sun by a factor of 10, 100, or 1,000. So the expectation was that if you could study these stars, that the convection, which is the cause of the waves, is the convection noise, that there would be waves excited, and these waves would reach a finite amplitude, and we'd detect them. That was the hope, okay? And from the ground, it was a really hard problem. And I'm not going to give you the history of it, but many people did fantastic work to try to detect this from the ground, but it's just really hard. And then you go into space and boom, everything pops out. So here's the first detection from Corot. So let me show you each of these a little bit. Each panel going across is a different star with some totally meaningless name. On this axis is shown the frequency of this is brightness. All you're measuring is the brightness of the star. So these aren't Doppler shifts, it's just brightness. This is then just the power spectral density, which is how much amplitude of noise is there at a certain frequency. And they have ordered them in this figure in increasing frequency. So each of these stars is a different star, but basically every giant showed oscillations. The amplitudes are 3 to 200 parts per million. These modes, if the star were to stop convecting and stop pumping them, which would never happen, these modes would just decay in 30 days. So they're not pure, they're not they're excited, they're at finite amplitude because they're getting pumped, okay? So this was remarkable because you put a mission in space, you can do this and it just falls in your lap. But obviously Kepler did the same. So I'm going to show you just a few of these power spectral densities. But again, you can see these uniformly spaced frequencies. This is the Kepler satellite. Again, this was back in 2010 now. These are different stars observed by Kepler. So each coordinate, these are just the Kepler input catalog numbers. Again, it's just a coordinate. It doesn't really matter for this talk. But again, you can see two things, I hope. One is you can see that there's some uniform frequency. There's some not interference, there's intermingling of different L's, L of 0, 1, and 2. But you also might notice that, let's say this star has a lot of power amplitude at this frequency, 250 microhertz. This star has nothing. So there is both the frequency spacing and evidence of this maximum frequency, that above some frequency, there's nothing going on in the star. And that's because of this fact that the high frequency waves will end up getting damped to the point where they can't get to high amplitude. So all the phenomenology we see for the sun is manifesting in all of these giant stars. It's just the frequencies have all shifted because the star is bigger, okay? But I don't want to belittle it, but that's about it. I mean, that's a lot of what's been done. I mean, there's been tremendous work done, but that's most of how you understand it. So you can take the Kepler data and you can fold it on the frequency spacing. And now I can answer the question that I couldn't answer for the sun only because of my ignorance. But this is the number of radial nodes. So this is 10, 11, 12, 13. That's how many nodes there are in the wave as you go into the star, okay? And so you measure the frequency spacing just straight away. And the typical number of nodes for these stars is there's 10 or 15, right? So you see a lot of waves, and you see L of 0, L of 1, L of 2. You also see something that's perhaps not surprising, which is the relative intensity, the amplitude of this variability. How loud is it? Depends on how bright the star is. And so again, this is a nice slide from Daniel Huber showing that as the stars are getting bigger and bigger and brighter, the amplitude of the variability, the light curve, how much variability is there? It gets larger and larger and larger. And that's just that the convection is more vigorous and allows for larger amplitude waves to be excited. So this plot is far too busy, but I have to show it because it's just an astonishing plot from the Kepler satellite. Each of these points is a red giant in our galaxy. They are showing where they are in luminosity in solar units. So the sun is down here. They're showing the surface temperature on this axis. And the color of the symbol is in parts per million. How much does the brightness vary? Okay, so in terms of what you can do from the ground, you could maybe get some of these from the ground, and that's it. In terms of and these have been studied from the ground, but all of these stars you're seeing here, you could never do from the ground. This little inset is showing all the stars for which it had been done from the ground laboriously by many people over many decades. And as often happens in science, when you build a new instrument, you very quickly go from having 15 data points to 15,000 data points. And that makes it really, really exciting. So let me pause there, and then I've just got a few more slides. And I want to talk about what we're using this for, right? But basically, we are able to measure the mass and the radius now for tens of thousands of red giants around the galaxy. And I'm going to show you the outcome of that, but I want to pause at this point, Reza, and see if there's other questions.
Sure. First, about the Kepler data, we have a question on how do you get the power versus frequency graph from Kepler data? Does it have a spectrograph to provide this data?
No. So what Kepler's measuring is the brightness of a star at some time interval. Depends on how the instrument was set up, but there's different cadences of observation. So the data are the brightness as a function of time. So the frequency you're seeing here is if you fold that data at this frequency. So this is what we call a Fourier transform of the time series. So when you see a peak at some frequency like this peak, it means that if you were to fold the data at this frequency, there would be a really big sine wave.
Okay, excellent. And you did mention this, but just to clear it out, maybe you provide more explanation. We have another question on the relationship between the size of the star and the speed of sound in them, given that they're going to have a different composition, and you mentioned different convection size layers.
So the time it takes the sound wave to go around the star or through the star, it's about the same. If they're all the same mass, then it completely depends on the radius. So the bigger the star, the longer it takes the sound wave to get through it, and therefore the lower the frequency of the waves. So these stars are these could be, some of these could be day long, or for the stars that are way up here, some of these periods are 50 or 100 days, the actual period of the oscillation, right? Which is another reason it's hard to do it from the ground. It's hard to do reliable photometry on that time scale. But in space, you can do that.
Okay, and how about the different composition of the core depending on the size? So the amount of helium they have in the center or other elements.
Yeah, that's a great question. So all I'm talking about right now are the waves that really live in the big giant envelope. There are waves that live deep within this helium core. And in the interest of time, because I don't really want to give a 3-hour talk, I'm not talking about those waves, but I will tell you that they have been detected. And the properties of those waves have actually been able to tell us what's going on in the helium core. We've been able to measure its rotation, its magnetic field, and whether it's burning or quiescent. So it's quite remarkable what we've been able to learn. And from the waves that live within the core that do manifest at the surface, quite astonishingly, they do manifest at the surface. That's how we're seeing them. So that's a great question. And I could say is yes, it's an active field, and that's been the most, that's where been, for me as a stellar physicist, the sort of most exciting surprises.
Thank you. And yeah, we have a question about this graph. Right between the red and green looks like there's a gap. Is there an explanation for that?
Some of this just has to do with the population of stars that were in the sample, and also what's called the Hertzsprung gap, which is that stars don't live here for very long. So, yeah. Right.
And the next question involves Kepler again. How many frames per second does Kepler collect data?
Oh, the cadence for Kepler, it's not frames per second, it's typically many minute long exposures.
Okay, and you have mentioned working for red giants. If you had sufficient aperture and cadence in space, can the technique work on dwarf stars?
Yeah, the time scales are much shorter. Obviously they're fainter, and so it really hasn't been possible with the current instruments. So yes, it should be happening in dwarfs. They're especially if you go to dwarfs that are like 20% the mass of the sun. They're fully convective. They should have these modes. They'd be very low amplitude, and yeah, we just haven't been able to do it.
Okay, thank you. Those are the questions so far.
Okay, great.
Can I ask a question? I've noticed in the LIGO experiment in gravity waves has been working in the microhertz and below region and finding good results. Is there any connection between microhertz in the resonance of the stars and gravity waves?
Yeah, so the LIGO instrument, its frequency range for gravitational waves is actually more like 10 hertz to 1 kilohertz, much higher frequencies. And yeah, there's no real connection to this for LIGO. Yeah.
And then to follow on, when you're talking about a microhertz, how long is that wavelength physically? The sine wave?
Oh, it's the size of the star. So 100 solar radius.
Oof.
The acoustic wave, yeah. Yeah. Okay, so you can take all of these data, you can measure for all these stars that frequency spacing and that maximum frequency. And from that, you can then get the mass and the radius, okay? So for a star that you have the brightness of on the sky, and you know its luminosity, sorry, and you know its surface temperature, pardon me. You know that L is 4 pi r squared sigma t to the fourth, but you know its apparent brightness goes like 1 over distance squared, okay? If I tell you the radius, you now actually have the absolute brightness of the star, which means you can calculate the distance. Okay, so by measuring the radius of the star, I can now tell you that star is that far away. And that's profound. In astronomy, we never know how far something is. So that's great. That's part one. So astroseismically, you can get a distance. Now, how else can we measure distances? Well, the conventional way to measure distances of the star is its parallax, right? The apparent motion on the sky 6 months apart. But of course, the Gaia satellite is doing much better than that and is measuring parallaxes to high accuracy. So there's a confirmation check, or more importantly, a prediction. That has worked out beautifully. So here's a beautiful plot from Joel Zinn, who's presently at the American Museum of Natural History, who's a graduate student at Ohio State University, showing the seismic distance inferred, the distance inferred from seismology on this axis, and the distance of Gaia. So this is two different pieces of physics, right? One is seismology, the other is parallax. Parallax is geometry, so it's basically hard to get it wrong. And you can see here how well they agree. And then you can see here the difference, pardon me. So this is a 5 to 10% measurement, right? That's fantastic. Okay, so from these two frequencies, and by knowing the surface temperature, because you've done spectra of the star and you have its brightness, you can get the distance. So here's what the stars are. So here's this is from K2, which was a follow-on mission, Kepler mission, sourced a different way. Again, another nice plot from Joel Zinn, which he was kind enough to share with me today, because I wanted to get updated work from him, just showing as the Kepler satellite looked in different directions. So these little spikes are just the field of view and they looked, right? So it's not that there's only stars there, but you can really see, this is now the Z coordinate. So the galactic plane is here, going up is this direction. You can really see, no surprise, there's more stars in the plane. This is not just dilution due to that. And then the TESS satellite, which is, many of you have heard about, is a satellite that NASA launched now about, I want to say 3 years ago, is also doing the same work. And again, it's now getting distances. These are much closer giants. TESS is a smaller aperture telescope than Kepler. You can do the same science, but not for stars as far away. That's why the scale here is changed. But basically, you're getting all these distances to all these stars. So not only do you get the distance, you get the radius, you get the mass. If you give me the mass and the radius, I can give you the age. That's pretty profound. I can tell you that star that far away is 2 gigayears old. That you never typically get. So it's a pretty exciting field. And let me just wrap up here with my final slide, which, this keeps growing. TESS keeps working. The data from Kepler is still being analyzed. The impact's quite broad. You can understand galactic structure. You can understand how the galaxy was constructed. You can use it to study stellar physics like rotation and magnetism. And for myself as a theorist, I want to remind everybody that to get from that squiggly line, which are the data, to the physical inference of these properties, mass, distance, rotation, age, magnetic field, that requires theoretical understanding of stars. And that's what I strive to do every day. So thank you all for coming this evening. Over to you, Reza.
Thank you very much. That was astonishing. Great talk and great science here. So now the floor is even more open for all the questions. First of all, about noise reduction. Somebody wants to know, how do you distinguish between sound waves in stars and electrical noise in the CCD sensor?
Because it's periodic. So it's the, this noise, so I'm not an instrument specialist for Kepler, so I can't answer where the instrument noise is, but all we're doing for this study is really understanding these strong spikes. Yeah.
Thank you. And somebody is asking about some exotic objects. Can we detect acoustics of black holes?
No.
Okay. And since you mentioned you are a theorist and you provided foundation for all these work to do, how long has it been that we have started to get this detailed information from the stars? You mentioned that the Kepler was for 2006. Where did the theory finalize, and when we actually started getting all these cool data about these stars?
So I would say really the Kepler satellite and the data from that and the astroseismic community that had been convened, which I was not part of, really made this tremendous progress and breakthroughs because of being able to do so many stars. So the field before that was very focused on the sun. That's where many people sort of cut their teeth on the sun, shall we say. And then there's some stars in the galaxy for which you can do this, but nowhere near the scale of measurements that we have today. So the field has really come to life in the last decade due to Kepler and Corot before that, a few years before that, the French mission. And now TESS is going great guns. The Europeans have a satellite called Plato, which will also be doing this. And, I have to say it because it's why many of these missions were funded. The search for planets around other stars is the driver for these missions. So I jokingly say, this is the science you should care about. But really, right, the reason those missions, their prime mission is to detect planets around other stars via transits. But, most planets aren't in the plane, right? So if you observe that, here you're batting 100% for every giant you look at. So it's a little bit more exciting from my perspective.
Thank you. And do you know if the Gaia's cadence is high enough to allow the technique for the whole sky?
No, so Gaia is doing astrometry, it's not doing this type of photometry. So the present mission that is doing astroseismology is the TESS satellite. That was a satellite designed and built by a group at MIT. It's a NASA mission. That's the current operating satellite for doing astroseismology. It's many small telescopes, but it's doing the whole sky. So Kepler stared at just certain small patches, very large aperture telescope, but smaller field of view. TESS is the opposite. It's smaller aperture telescopes, large field of view, and it's doing swaths of the sky, and then it rotates and does another swath. It doesn't go as faint, but it's getting, just as many stars. So it's pretty exciting right now what's happening with TESS.
Thank you. And we are not able to resolve the individual stars in other galaxies. So all we're talking about are the stars in our own galaxy. So the question is, how big of a telescope do we need to be able to do this kind of analysis for stars in other galaxies?
It's a great question. So you can do astroseismology of stars in other galaxies, but you have to find the stars that are very bright. So what are called red supergiants, which have luminosities about 100 times brighter than this. In something like Andromeda, you can see pulsations. They're very large amplitude. So now we're talking the brightness of the star changing by 10%. So you can do it. We actually collaborated with the Palomar Transient Factory to do that work to detect oscillations, typically 100 to 200 day periods. But those stars are 19th to 20th magnitude, but it's possible. And of course, Cepheids, which is a very special pulsation, radial pulsations, very large amplitude, have been used for distance measurements for a long, long time, right? So the Cepheids have been part of the distance ladder for cosmology for, a long time.
Okay, thank you. And what would it be like if we do the same kind of observation with quasars? Is that possible?
Yeah, well, so quasars, we pretty confident now are black holes at the center of distant galaxies, where what you're seeing is light associated with matter that's circulating around the black hole. Now and again, they'll show periodic phenomena, but now you're trying to understand the sort of seismology of the accretion disk. So when somebody asked about black holes and I said no, the only thing you might be able to do would be the seismology of the accretion disk, but we haven't had much luck with that. You typically just see one period, and it's pretty hard to unravel the cause of a period if you only have one period. So, you need to see patterns, and you don't get a pattern out of one.
Thank you. And we have a person who's asking for more explanation on the photoacoustic spectrum.
So maybe they're asking about this. I'm not sure if that's how I interpret the spectrum. So again, all of the measurements I'm showing here that are not for the sun, what you're measuring is literally just the brightness of the star, and you're just making a plot of the function of time. That's the data. Okay. And when I show frequency here, it's if I take that data and now I fold it at this frequency, when I see a spike at this frequency, it's because if I fold at that frequency, I would get a nice sine wave. If I folded a frequency that's off, it would just be mush. That's a technical term.
Okay, thank you. And somebody wants to know if this technique be used to see if a star is ejecting too much material for the life to survive on a planet around it.
Yeah, so these stars, as they go up the red giant branch, we have been asking for many, many years, do they lose mass? if you look in an open cluster, you can see stars that have gone up and have returned to what's called the red clump or the horizontal branch. And so we have been able to measure the masses of those stars, which are a little bit later in their lives of evolution. And because we measured stars going up and these stars that are sitting on the clump, we can ask how much mass was lost. And that's a measurement that you can only make with astroseismology that shows there's very little mass loss. And that was a bit of a surprise.
Okay, thank you. And back to a question that I asked earlier, and you did mention that there are all these kind of waves that are happening on a star. The smaller wavelengths, waves of the sun, we are able to observe, but we can only observe those waves that have the longer wavelengths, which pass through the core of the star from the far away stars we can observe. But in terms of that Doppler shift we see on the surface of the sun, for the surfers among us, how many kilometers does the surface of the sun go in and out?
Oh, I don't know that. I don't know that. We could calculate it. So the velocities are about 0.5 kilometer per second, if I have it right. Yeah, it's about 0.5 kilometer per second. And so the velocity is the frequency times the amplitude.
Okay.
Okay, so you just write V is omega times R, and for omega, write 2 pi over 250 seconds times the amplitude. So you 0.5 kilometer per second equals 2 pi divided by 250 seconds times the amplitude, and that'll give you the motion. That'll give you the actual amplitude. The displacement, what we call the displacement. How much is it moving?
Okay, excellent. Thank you. So I'm gonna do that after the meeting. Thanks. And there is a question about saying that the pixel size of tests is quite large. How do you screen data to remove confusion from other sources in the pixel?
Very carefully. That's a great question, and it's a real challenge for tests for sure. The only experience I have as a theorist, I do collaborate with observers, and I'm presently collaborating with excellent observer Mai Pedersen, who's a postdoc at the KITP, who's actively looking at massive stars with tests. The advantage of that is that they're very rare and they're very bright. So that helps with that challenge because it's unlikely to have another bright star in the pixel. So yeah, there is an ultimate confusion limit. And if the other stars aren't oscillating at finite frequencies, it just increases your broadband noise, but it doesn't mess up your frequency measurement. So it does inhibit the measurements for sure, though.
Thank you. And back again, referring to a previous question about stars losing mass. Can this technique be also used to estimate the amount of coronal mass ejections around a distant star? Not the mass of the star, but how much matter it's ejecting?
Yeah, we don't really see in the giants. Short answer is no. We don't have a good probe of that. The frequencies aren't that stable, so it's pretty hard. Yeah, short answer is no.
Okay, thank you. And back to a question that has been asked several times. I think it hasn't been clear yet. So sure. What does cause these waves to appear to begin with?
Okay. So there's two ways to excite a wave in a star. One is to have a heat engine that is frequency matched to a wave. That's what happens in the Cepheids. That's not what I'm talking about here tonight. What happens in the sun and all of these red giants is different. It's the fact that there's a large volume of the star, which is this convection zone, where the fluid is actively moving, okay? This generates acoustic waves of all frequencies. So it's this very loud, noisy environment, but you would call it broadband noise, right? I'm not going to tell you whether it's red noise or white noise, but it's noise, okay? But that means that at every frequency, there's a little bit of power, there's a little bit of excitation. So if you have a well-defined high response, right? I can I can ring my glass, right? There's a frequency it's ringing at, right? That's a natural frequency for my glass to ring at. And if I do something else, it'll ring at a different frequency, right? I'm putting nodes, you can't see it, but I'm putting nodes at different locations. So what's happening in these stars is the convection is providing the opportunity for excitation, and the star ends up getting finite amplitude in all of these modes that it wants to ring at. So
okay, excellent. I thank you very much. I think that clears it up.
I'm not sure. It's a hard, we can't calculate it. People can. It's a hard problem theoretically, for sure. So.
And so now we have a question about Betelgeuse, that it was observed that there was a decline in the luminosity recently.
Yes.
And there was a lot of question if that means it has gone supernova by now. Is the resolution of this question of when it goes supernova, can it be done with this kind of analysis and the
all red supergiants like Betelgeuse oscillate, and Betelgeuse is doing what it should given the type of star it is. And the recent fading, it's come back. I don't really track it anymore, but I did have one of my grad students who worked on that, Jared Goldberg, with a few other people. But it's things happen, but it's not about, it didn't blow up.
Okay, thank you. And we have another question that's again understanding wise. So probably they need more explanation. And because you said these are sound waves on the surface, and they would need, how do we relate that again with the luminosity of the sun or the star to see that, or the detection of these things? If you can explain more on that.
Right. So when I say they're a sound wave, what I'm really saying is that what's the restoring force to the motion is the pushback of trying to compress the plasma. Okay, that's what defines it as a sound wave. So if you think of it at the surface, if you have a large wave and you get a big compression, it's going to get a little bit hotter at the surface because of the compression, and it's going to radiate a little bit more. And then when it decompresses, it gets cooler and it's going to radiate less. So you do change the brightness of the star directly, just due to the sound wave.
Thank you. So basically, to rephrase what you says is that this compression on the surface causes the change in luminosity, and that's how we observe them. Basically, the change in the electromagnetic radiation. Thank you. And now looks like we've gone through all the questions. One other question, because you're all on the board of directors of the Las Cumbres Observatory, and we actually have a program in our club, the Cosmic Adventures, which we use your educational telescopes to actually do some exoplanets and other research. So I would be excited if you tell us a little bit about the Las Cumbres Observatory, the science you do there, and also your education program.
Yeah, well, the education program is going great guns. I encourage all of you to go to the website and look. We've modified in the last few years. Edward Gomez is the member of the staff who really is running that program. We're really working to provide telescope time to well-organized groups who have a mission. So I'm glad to hear that's happening. The 1 meter telescopes are the prime science drivers for the observatory. We have two that are may have arrived in Tenerife by now. I'm not sure. They were put on a boat a while back. It takes a while to get there. That will start to complete the northern ring. So we have telescopes in South Africa, Chile, and Australia. But the ones in the Tenerife, we now also have one in West Texas that's been there for a while. And eventually, there'll hopefully be some in China. We'll then complete the northern ring so that we have basically a northern and a southern ring of the 1 meter. And of course, there's two 2 meter telescopes, one in Hawaii and one in Australia that were the original Falks telescopes. So it's a going venture. It's going well. There's been instrumental upgrades over time. There's high resolution spectroscopy now available on many of them. And yeah, I'd really encourage people to find a way to get engaged with the education program as well as the science. It's been a pretty exciting endeavor. I got involved because the founder, Wayne Rosing, chose to base it here in Santa Barbara. And so I've been involved since he came to town, and I've had the real privilege of working with him and all of the great scientists at the observatory who've been doing remarkable things now for almost 15 years.
Excellent. Thank you very much. And let me emphasize that all OCA members, if they're interested to have access to Las Cumbres remote observatories, they are actually, as Dr. Bilson mentioned, they're located all around the globe. So we do have access to Saturn skies too. You could get through Cosmic Adventures program. You go check our website and you can sign up there, and we'll give you access to the Las Cumbres Observatory, and you could do some real science, especially exoplanets we're doing right now. And we are about at the end of our time, but there is just one question I would like to combine them together to ask you, and that's about these coronal mass ejections again and solar flares. Could combination of different quote unquote ringing modes on the sun be cause of these kind of activity, or is there separate process for them?
No, we know in the sun that these are all really having to do with the magnetic fields on the sun. Okay. So the waves are not the cause of those events. The origin of those has to do with the evolution of the magnetic field in the convection zone of the sun. So very different phenomena. Yeah.
Okay, thank you again very much, Dr. Bilson. That was a fabulous talk. We really enjoyed this interactivity and you taking patience to answer all our questions.
I really enjoyed it.
Yes, a lot of audience feel the same way. Again, let me mention that we're going to continue our online meetings. Please check the calendar on our website for all our upcoming events at ocastronomers.org. And also, if you're interested to take part in some actual research, you could check out Cosmic Adventures. This, I would like to thank everybody for participating and attending. See you all next month. Have a great time ahead. Bye.